Good afternoon and welcome to your science review with Mr. Blades. You can see now that we have a combination circuit that we're looking at here. I've already filled in all the information that we have from our problem statement, our resistances, and our 20 volt power source. Now you can see that we have a resistor in series with the battery. We have two resistors in series as one part of a parallel circuit branch, and then we have two resistors again in parallel on the other side of that parallel branch. So let's go ahead and start working this out piece by piece. Now I've reminded you guys multiple times that our first step is to simplify as much as we can. So what we're going to do is we're going to combine these two resistances to get the resistance in this branch. We're going to combine these two resistances to get the resistance in this branch, and then we're going to combine the resistances of this entire parallel circuit together, then with the series resistor. So let's go ahead and get started. Now R4, 5 is going to be easiest because since R4 and 5 are in series, we're just going to go ahead and add them together. R4 plus R5, which is 20 plus 15, or 35. Now R23 is a little bit different because since it's in parallel, we're going to go ahead and do our R23 is equal to 1 over R2 plus 1 over R3, or 1 over 6 plus 1 over 10. Now if I add that together on my calculator, 1 divided by 6 plus 1 divided by 10, we end up with 0.266. And if we take the reciprocal of both sides, we get R23 is equal to 3.75 ohms. Now keep these in mind because we're going to need to use them later. Now those are the resistances in each one of our parallel branches. So what we have now is we're imagining a left side with one resistor in it and a right side with one resistor in it. But these two are still in parallel. So let's go ahead and do R2, 3, 4, 5. Since it's in a parallel configuration, we're still going to do 1 over R2 plus 1 over R4, 5 is equal to 1 over R2, 3, 4, 5. And since we already did that, we ended up with 1 over R23, which is 0.266 from down here, remember, plus 1 over 35. That gives us 0.295 ohms, or take the reciprocal of both sides, and we end up with R2, 3, 4, 5 is equal to 3.39. Now, we should take a moment to pay attention to the fact that this is lower than that, which is lower than that, and lower than all of the ones in the parallel piece. So our math is at least checked. And now we can add up our resistances and find our R total. Don't forget we reimagined this as one resistor, these two as one resistor, and then our entire parallel configuration here as one resistor. And that is in series with R1. So we can go ahead and just find our R total, or our R1, 2, 3, 4, 5, by adding R1 to R2, 3, 4, 5, or 5 plus 3.39, and that gives us 8.39 ohms of resistance. Okay, so now we can go ahead and use our Ohm's law, V equals IR, reconfigured to give us our I, or V over R, because according to our table, the only thing we know enough about to calculate is the current through the entire system. So V20 divided by 8.39, which gives us a current of 2.38. All right, now let's continue. Now, since we have simplified this down to imagine in our minds one battery and one resistor, we've already done that and we've gone as far as we can with that particular imagining. What we're going to have to do now is we're going to have to start breaking it back out. So now what we have is, in our minds, we have our battery, R1, and our R2, 3, 4, 5. Okay? So we can calculate the voltage for R1 by realizing that we have this in series with all of this. And our voltages in a series circuit add up. So our V1, our voltage for the first one, is going to be I1 times R1. And because we have our imagined series circuit right now, we can also move our total current, 2.38, up here to I1, because everywhere in a series circuit the current is the same. So our V1 is going to be equal to 2.38 times 5, or 11.92 volts. Okay, so this resistor right here uses up 11.92 volts, and the voltage left over for this entire parallel circuit is, let's say V2, 3, 4, 5, is equal to 20 minus 11.92, or 8.08 volts. That's all that's left for this one. Now don't forget, that means that the voltage is the same in this side and in this side. So 8.8 volts is over here, and 8.8 volts is over here. Okay? Now because of that, we know that R2 and R3 are going to have the same voltage as everywhere else in that parallel circuit, or 8.08. And R3 is going to have a voltage of 8.08. Okay, apologize for my handwriting. Now we can go ahead and calculate the current through each one of those, right? So I2 is equal to V2 over R2, or 8.08 divided by 6, or 1.35. Same deal, I3 is V3 over R3, or 8.08 divided by 10, or 0.808 amps. Okay, so now we need to figure out our voltage and our current through the right side of this parallel circuit. Now, we know from this parallel circuit that the current running through the left side plus the current running through the right side has to equal the total current in the circuit, or 2.38 amps. Now, the way we figure that out is I45 for the right side is equal to this 2.38 minus the current running through the left side, or 1.35 minus 0.808. That gives us 0.222 amps. Okay? Now, in order to find out the voltage, well, and actually, since we know the current running through the right side here, and these two are in series with each other, we know that their current must be the same. Now we can go ahead and calculate our voltages. V4 is I4 times R4, or 0.222 times 20, and that gives us 4.44 volts. Next, V5 is equal to I5 R5, which is 0.222 times 15, or 3.33. Now, I know these two add together, and these two should add to this one. These don't quite, and the reason is because there is a lot of rounding happening here, here, a lot of rounding here, 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 and everywhere. And after doing 5 or 6 calculations and rounding all of them, what we end up with is a little bit of discrepancy between what we expect to see in our actual problem and what we actually get. This kind of rounding error will not keep you from getting the right answers in the test. But that is why we show all of our work. Because if I'm grading your quiz, I can see that you have in fact done everything right. It's just that these answers came out a little strange. Okay? So I hope this was helpful, and I'll see you in class.